Hello students, I am Pei Zhang from Tianjin University and IEEE Fellow. I work on power system operation, intelligent computation, and carbon-aware dispatch. In this micro course, I explain the real-time electricity-carbon coupling relationship of coal-fired power plants. The word coupling is important. I am not only asking how much carbon dioxide a plant emits over a month or a year. I am asking how the instantaneous generation output, fuel consumption, equipment efficiency, and carbon dioxide mass emission rate move together during operation. The cover introduces two scientific viewpoints. A Newtonian paradigm starts from physical mechanisms, coal combustion, boiler heat transfer, turbine conversion, generator efficiency, and material balance. A Keplerian paradigm starts from observed operating data and fits the relationship directly. My goal is to show why these two viewpoints should be integrated. A dispatch center needs carbon information at the same time scale as power control, and that information must be fast, interpretable, and accurate enough for engineering decisions. The course is organized in 4 parts. The first part explains why electricity-carbon coupling matters for coal-fired units. The second part develops the method. I separate the coal-to-electricity process, the coal-to-carbon dioxide process, and the direct electricity-to-carbon relationship. That separation prevents a common mistake, treating carbon emissions as a fixed number per kilowatt hour while ignoring changing efficiency and fuel properties. The third part uses plant data as a case study. It compares the coefficient obtained from the mechanistic model with the coefficient obtained from real-time data fitting. It also checks how the sampling interval affects the fitted relationship. The fourth part draws the operational conclusions. The final message is practical. Carbon-aware dispatch needs a coefficient that can be calculated in real time, updated from actual operating data, and explained through the equipment physics of the unit. The background numbers explain the urgency. Energy activities account for about 88% of China's carbon dioxide emissions, and the power industry contributes about 41% within that energy sector footprint. The installed capacity chart also reminds me that China is diversifying rapidly, with wind, solar, hydro, and nuclear capacity expanding, but thermal power remains deeply embedded in electricity supply. By the end of 2023, thermal generation still represented nearly 70% of annual electricity output. That means carbon management cannot wait for a future system with no coal units. It has to work inside the current operating system. Annual average emission factors are useful for inventories, but they are too coarse for dispatch. A coal unit at different loads can have different heat rates and different effective carbon intensity. If the grid wants to coordinate economic dispatch and carbon reduction, the carbon signal must follow operating conditions. This page motivates a real-time model rather than a static accounting factor. The business implication is also clear. When a dispatch decision moves output from one unit to another, the carbon effect is not only the difference between two published average factors, it depends on the current load, the current fuel batch, and the current efficiency state. Real-time coupling turns carbon from an accounting result into an operational variable. 3 carbon measurement methods are compared because each one answers a different engineering need. The emission factor approach is easy to apply. It multiplies fuel use or electricity output by a prescribed factor, so it is practical for inventories and reporting. Its weakness is that the factor is usually fixed or slowly updated, so it cannot represent a unit whose efficiency changes with load. The carbon balance method follows material conservation. It tracks carbon entering with coal and carbon leaving through combustion products, slag, ash, and desulfurization-related paths. This is more mechanistic, but it needs reliable fuel properties and process data. The online monitoring method measures flue gas concentration and flow in real time. It is closest to the operating signal needed by dispatch, but instrumentation error, calibration, missing data, and system cost must be handled. The research problem sits between these methods. I want the physical credibility of carbon balance and the time resolution of online monitoring, while keeping the result suitable for coordinated electricity carbon dispatch. For an operator, the method also has to be explainable. If a carbon signal changes suddenly, the plant should know whether the cause is coal quality, load level, boiler performance, sensor drift, or a data gap. A useful model must therefore separate measurement from diagnosis. The 2 research paradigms define the logic of the course. The Keplerian paradigm begins with observation. It looks at data, identifies stable patterns, and builds empirical relationships. In this topic, the data are real-time generation output, and measured carbon dioxide mass emission rates. The advantage is that the fitted relationship directly reflects actual plant behavior, including effects that may be hard to model explicitly. The weakness is generalizability. A fitted curve may describe one operating period well, but may not explain why the coefficient changes. The Newtonian paradigm begins with theory. It writes the plant as a chain of physical transformations and derives the relationship from energy conversion and material balance. Its advantage is interpretability. Its weakness is that every uncertain parameter, from coal quality to equipment efficiency, can affect the result. I use both paradigms because dispatch decisions need the confidence of physical causality and the calibration power of real measurements. The method framework separates the problem into three functions. The first function maps coal to electricity. It describes how chemical energy in coal becomes heat in the boiler, mechanical power in the turbine, and electrical output in the generator. The second function maps coal to carbon dioxide. It includes carbon oxidation during combustion and the smaller desulfurization-related carbon dioxide path. Once both functions share the same fuel consumption variable, I can eliminate that variable and obtain the direct relationship between electricity and carbon dioxide. That is the Newtonian route. The Keplerian route starts from measured data. It takes real-time generation power and measured carbon dioxide emission rate, then fits a direct function between them. The bottom of the framework is the comparison step. If the mechanistic coefficient and the fitted coefficient agree, the model has both physical support and empirical support. If they differ, the difference points to fuel content, boiler efficiency, turbine efficiency, or measurement issues. The coal-to-electricity diagram is the physical backbone of the Newtonian model. Coal enters through the feeder and coal mill, then chemical energy is released in the boiler. The boiler transfers heat to water and steam, creating high-energy steam that drives the turbine. The turbine converts thermal energy into mechanical shaft power, and the generator converts shaft power into electrical output. The condenser, cooling water system, reheater, and flue gas path are not secondary details. They determine the actual efficiency of the unit. Ash, slag, sulfur dioxide control, and stack emissions also connect the electricity side to the carbon side. The important engineering judgment is that power generation is not proportional to coal consumption through a universal constant. The coefficient depends on lower heating value, boiler thermal efficiency, pipeline efficiency, turbine internal efficiency, mechanical efficiency, and generator efficiency. The same coal flow can produce different electrical output if the unit operates at different efficiency. The main equation expresses generation output as fuel consumption multiplied by lower heating value and by the conversion efficiencies of the plant. B is the coal consumption rate. Q net P is the lower heating value of the fuel. Eta B is boiler thermal efficiency, eta P is pipeline efficiency, eta I is the absolute internal efficiency of the steam turbine, eta M is mechanical efficiency, and eta G is generator efficiency. The factor 1/3600 converts heat energy into electrical energy units. The diagram on the right gives the same idea as an energy chain. Heat enters the boiler, steam delivers thermal energy to the turbine, internal power becomes shaft power, and shaft power becomes electrical output. For modern units, boiler efficiency is often around 92.5 to 94%. Pipeline, mechanical, and generator efficiencies can be close to 99%. Turbine internal efficiency is much more variable. That is why changes in operating condition can shift the electricity carbon coefficient even when the plant and fuel appear unchanged. The product form of the equation is useful because it shows sensitivity. A small relative change in any efficiency changes the final electrical output. If the carbon side stays almost unchanged while the electricity side improves, the same fuel carbon is spread over more electrical output, and the coefficient falls. This is the physical source of load-dependent carbon intensity. The coal-to-carbon dioxide model has two emission paths. The first pass is fuel combustion. Carbon contained in the as-received coal is oxidized, and the molecular weight ratio 44/12 converts carbon mass into carbon dioxide mass. The formula uses BCr-OFC, and the ratio 44/12. Cr can also be linked to lower heating value and carbon content per unit calorific value. The second pass is desulfurization. Carbon dioxide can be generated during the desulfurization process, and the formula uses sulfur content Sr, sulfur oxidation rate OFS, desulfurization efficiency eta SO2, and the ratio 44/32. In most coal-fired units, the combustion path dominates. Desulfurization emissions are usually small, but omitting them would make the accounting logic incomplete. This page is valuable because it ties the carbon coefficient to measurable fuel properties. Carbon content, oxidation rate, sulfur content, and heating value are not abstract parameters. They are plant management variables that affect carbon accounting. The derivation uses fuel consumption as the hidden bridge between power and carbon dioxide. In the first box, once lower heating value and efficiencies are specified, generation power can be approximated as kBE times coal consumption. In the second box, the carbon dioxide mass emission rate can be approximated as kBC times coal consumption. kBC includes the combustion carbon term and the desulfurization term. Dividing the carbon side coefficient by the electricity side coefficient eliminates coal consumption. The bottom formula states that the real-time carbon dioxide mass emission rate equals KEC times real-time generation power. This is the key coupling equation. Its simplicity is useful for dispatch, but the coefficient is not arbitrary. It is the ratio of a carbon emission mechanism to an electricity conversion mechanism. If fuel carbon content rises, KEC rises. If unit efficiency improves, KEC falls. The equation gives dispatch a real-time carbon slope that can be interpreted physically. It also creates a clean interface with optimization. A dispatcher does not need to solve the full boiler and turbine model inside every dispatch interval. The detailed plant model can update KEC, and the dispatch model can use that coefficient as the carbon slope for the current operating condition. The Keplerian path depends on two real-time data systems. The plant-level SIS collects process information from the operating unit. It connects monitoring, optimized control, production management, and links to lower-level distributed control and auxiliary control systems. For this research, SIS provides generation output and process variables needed to understand unit condition. The CO2 CEMS measures carbon dioxide concentration and emission-related flue gas parameters. It includes concentration monitoring, flue gas parameter monitoring, data acquisition and transmission, and sometimes ambient pressure monitoring. These systems make it possible to fit the electricity-carbon relationship without first specifying every physical parameter. In engineering terms, the fitted curve is a calibration channel. It captures how the plant actually behaved during the measurement period. The risk is that data quality, sensor calibration, missing points, and operating range coverage determine the credibility of the fitted relationship. Good data do not replace physics, but they can reveal whether the physics-based coefficient is realistic. The fitting method is least squares. The observed value Yi is the measured carbon dioxide mass emission rate. The independent variable Xi is generation power. The parameter vector beta defines the chosen function, such as a linear, quadratic, cubic, or exponential form. The ratio is the difference between the observed value and the model predicted value. Least squares chooses parameters that minimize the sum of squared ratios. This objective is simple, but it is appropriate for comparing candidate coupling functions under the same dataset. The metrics have different meanings. R squared tells how much variation in the measured emissions is explained by the model. Adjusted R squared penalizes unnecessary complexity, so it is useful when comparing linear and higher-order polynomial fits. RMSE measures error in the physical units of emission rate. A model with a slightly higher R squared but unnecessary higher-order terms may not be better for dispatch. For a dispatch coefficient, stability, interpretability, and error magnitude all matter. I therefore treat goodness of fit as an engineering screening tool, not as the only decision criterion. The preferred function should fit well, stay stable across sampling intervals, and retain a clear connection with plant physics. The Newtonian case study substitutes plant performance data and the fuel characteristic data into the derived coefficient. The table gives the key inputs. Q net P is 18,702 kilojoules per kilogram. Boiler efficiency is 92.5%. Pipeline, mechanical, and generator efficiencies are each taken as 99%. Turbine internal efficiency is 40.5%. The fuel carbon content is 50.1%. The carbon oxidation rate is 93%. sulfur content is 0.66%, and the desulfurization-related factors are set to 100%. With these values, the derived relationship remains first order. Carbon dioxide emission rate equals KEC times generation output. The calculated KEC is 0.9095. The engineering meaning is direct. Around this operating condition and the fuel quality, every additional megawatt of generation is associated with roughly this slope in carbon dioxide mass emission rate. The coefficient is not fitted from the scatter plot, it is produced by the physical chain. The data-driven case study uses 1-minute generation and carbon dioxide measurements. The scatter plot is dense and noisy, but the upward trend is clear. Higher generation output is associated with a higher carbon dioxide mass emission rate. The table compares linear, quadratic, and cubic functions. The linear model is y equals 0.9112x, with r squared about 0.8714 and RMSE about 10.89. The quadratic and cubic models improve r squared and RMSE, but their higher order coefficients are small. For dispatch, a simple linear coefficient has a strong advantage because it is transparent, stable, and easy to embed in an optimization model. The important comparison is with the Newtonian coefficient. The fitted linear coefficient is very close to the mechanistic value of 0.9095. That agreement supports the claim that the physical derivation captures the main operating relationship. The sampling frequency test asks whether the relationship is an artifact of the 1-minute data resolution. The result is reassuring. Across 1 minute, 5 minutes, 10 minutes, 15 minutes, 30 minutes, and 1 hour, the fitted function remains almost the same. The slope oscillates around 0.9112, and the maximum deviation is about 0.01%. The model is therefore not highly sensitive to the chosen acquisition interval. The error metrics improve as the interval becomes coarser. R squared rises from about 0.871 to about 0.888, while RMSE falls from about 10.89 to about 9.64. That pattern is expected because coarser averaging suppresses short-term fluctuations and measurement noise. For dispatch, the 15-minute interval is meaningful. It reduces fitting error and variability while still matching a timescale often used in market clearing, scheduling, and operational assessment. The influencing factor analysis explains why the two paradigms are close but not identical. The comparison between combustion and desulfurization emissions shows that combustion accounts for more than 99.5% of total carbon emissions. Desulfurization contributes less than 0.5%. That means most uncertainty in the carbon side coefficient comes from fuel carbon content and combustion-related assumptions, not from the desulfurization path. The second chart compares measured and calculated overall unit efficiency. The deviation is much more visible. That points to the electricity conversion side as a major source of discrepancy. Boiler efficiency and turbine internal efficiency change with operating conditions, aging, heat losses, and load level. A fixed efficiency assumption can therefore distort KEC. The practical conclusion is that real-time electricity carbon coupling should not rely only on constant parameter values. It needs dynamic efficiency estimation from plant process data calibrated by actual emissions measurements whenever possible. This diagnosis is important for management. If a plant wants to reduce carbon intensity, improving combustion control, maintaining heat transfer performance, and keeping the turbine closer to efficient operating regions can be as important as choosing a different accounting factor. The hybrid approach begins by making efficiency dynamic. Boiler thermal efficiency eta B is the ratio of boiler thermal load, QR, to the heat input from coal, B times Q net P. This ratio can be computed from SIS process data, instead of assumed as a constant. The longer QR expression accounts for several heat transfer terms: main steam, feed water related enthalpy differences, superheater behavior, and reheater behavior. The steam cycle schematic gives the physical reason: steam extraction, reheating, attemperation water, leakage losses, heater drains, and feed water flows all affect the useful thermal load. In real plants, reheater steam flow may not have a direct monitoring point. The bottom formula estimates the missing reheater flow term from other measurable parameters. This is a good example of Newtonian and Keplerian integration. The equation structure is physical, but the inputs are real-time measured or inferred operating data. The carbon calculation becomes more responsive to the actual condition of the unit. It also becomes auditable. When the coefficient changes, engineers can trace the change back to steam flow, enthalpy, leakage, or heat input rather than accepting a black box numerical adjustment. The remaining efficiency equations complete the electricity side of the coupling model. Pipeline efficiency eta P equals steam turbine heat consumption QSR divided by boiler thermal load QR. QSR is calculated from main steam, superheater, and reheater parameters, again using measured or inferred process variables. Turbine internal efficiency eta I equals 3600 times internal power PI divided by QSR. The factor 3600 keeps the power and heat units consistent. Mechanical efficiency eta M is shaft power PAX divided by internal turbine power PI, and generator efficiency eta G is electrical output E divided by shaft power PAX. These ratios form a cascade. Heat from fuel becomes useful boiler load. Useful steam energy enters the turbine. Internal turbine power becomes shaft power, and shaft power becomes electricity. When these efficiencies are calculated dynamically, KEC becomes a real-time operational coefficient rather than a fixed inventory factor. The hybrid case study shows the benefit of replacing fixed efficiency assumptions with dynamically computed process values. In the left chart, the measured overall unit efficiency varies strongly. The Newtonian parameter line is much flatter, while the hybrid Newtonian-Keplerian line follows the measured behavior more closely. In the right chart, the same improvement appears in the carbon dioxide emission mass rate. The error table quantifies the difference. The mean error drops from about 2.88 to about 0.54. Mean squared error falls from about 149.16 to about 81.70. RMSE falls from about 12.21 to about 9.04. The maximum error also decreases. This is the central engineering result of the course. Pure mechanism gives explainability, but fixed parameters can miss real operating variation. Data calibration improves accuracy, and the physical model keeps the result interpretable. The hybrid curve is not merely curve fitting on top of a plant diagram. It is a correction mechanism that lets measured operation update the physical coefficient while preserving the causal pathway from fuel to heat, heat to power, and fuel carbon to carbon dioxide. The conclusions can be summarized as operational rules. Under the normal generation range of the coal-fired unit, both the mechanistic derivation and the data-driven fitting support a near-linear electricity-carbon relationship. 15-minute sample data provide higher modeling accuracy and better suitability for real-time dispatch optimization than very high-frequency noisy measurements. The coefficient is influenced mainly by the as-received carbon content of coal, boiler thermal efficiency, and the absolute internal efficiency of the steam turbine. As generation output increases, the coefficient tends to decrease because the unit operates more efficiently. The hybrid Newtonian-Keplerian calculation aligns more closely with measured carbon dioxide emissions than a fixed parameter mechanistic calculation. For the grid, the implication is clear. Dispatch should not minimize cost alone and then calculate carbon afterward. Carbon emissions should enter dispatch decisions together with economic factors. A real-time coefficient makes that possible because it converts operating output into a carbon signal that is timely, interpretable, and measurable. The same idea can support plant benchmarking, unit commitment, carbon cost allocation, and post-event emission analysis, because all of those tasks need a coefficient that responds to actual operating conditions. A final case study diagnostic sharpens the conclusion about load dependence. Under stable operating conditions, as generation output increases, turbine heat rate decreases, and turbine efficiency improves. The electricity carbon coefficient KEC therefore declines. The two scatter plots put generation output on the horizontal axis and the measured coefficient on the vertical axis. The fitted curves slope downward, even though the point cloud is broad. The power law expression estimates KEC as 1.418 times E to the negative 0.07025. Multiplying by E gives the carbon dioxide emission rate approximation CE equals 1.418 times E to the 0.92975. The exponent below 1 means emissions still increase with output, but less than proportionally in this operating range. That result matters for dispatch. The marginal carbon effect of an additional megawatt depends on where the unit is operating, not only on its nameplate emission factor. I close with one practical message. Real-time electricity carbon coupling is a bridge between plant operation and a low-carbon dispatch. The Newtonian model explains how coal quality, boiler performance, turbine performance, and generator conversion create the coefficient. The Keplerian model checks that coefficient against measured operating data. The hybrid model updates efficiency dynamically and improves agreement with actual carbon dioxide emissions. For engineers and researchers, this means carbon accounting should move closer to the timescale of operation. For dispatch, it means economic objectives and carbon objectives can be evaluated together. Thank you.